Welcome to the Information Philosopher. I'm Bob Doyle, webcasting from my ITV studio in Cambridge, Massachusetts. I'm hoping to reach philosophers and scientists around the world to help solve some great problems in philosophy, in physics, in biology, and in psychology. I also hope to interest you who are curious about the deep nature of reality and our place in the universe. Today, this lecture will be about cosmology and our place in the universe. We live in the information age, but I find that very few philosophers or scientists understand the nature of information, especially the origin of information. Information is neither matter nor energy. It needs matter to be embodied in our brains, for example, and it needs energy to be communicated, like this lecture coming to you over the internet. But matter and energy are conserved quantities. It may be hard to believe, but the total amount of matter and energy today is the same as there was at the beginning of the universe, nearly 14 billion years ago. Okay, I am going to spend today with a departure from our last lectures. We're now in our third week of hourly lectures, Monday through Friday, and at 3 o'clock. And today's lecture is on philosophers and scientists. And this will be our first lecture on a scientist. In this case, it's going to be a Harvard colleague of mine named David Layzer, whose book on Cosmo Genesis talks to us about the origin of information in the universe. Let's just cut over to this view. Here's the book Cosmo Genesis, which was 1990, The Growth of Order in the Universe. So when I came to Harvard from Brown University, graduating there in physics in 1958, and entering as a graduate student in astrophysics, I learned that the model of the universe that was described at that time was thought to begin at that time maybe 10 billion years ago. We now have a much more accurate date for the beginning of all of these things that we're living in, as 13.75 billion years ago. But the conversation at Harvard and other universities teaching astrophysics was that the universe had begun in a state of equilibrium, a state of maximum entropy, maximum disorder, some 10 billion years ago. Now that seemed very curious to me at the time, because I had studied thermodynamics at Brown and learned well the so-called second law of thermodynamics. The first law, parenthetically, is to say that energy is conserved in thermodynamic terms, dealing with energy. But prior to that conservation law, there was a law known as the conservation of matter, that you cannot destroy or create matter. Well, ideas about that changed in the 20th century as especially Albert Einstein came to see that matter is indeed convertible into energy, that energy, when absorbed by matter, adds to the mass of the matter. And in particular, that energy in the form of light has a matter or material equivalent, and that means that it is subject to the force of gravity, so that when light tries to pass by a large object like the sun, it should curve, and in a way that ultimately is related to what Einstein described as the curvature of space, because light travels in straight lines, and if light bends when it travels around the sun, getting close and feeling the gravitational attraction of the sun, then space itself can be said to be curved in a famous picture that we have of general relativity. Now we have a conservation law for matter and a conservation law for energy, but we have a conservation law for the two combined once we realize that these can be converted into one another. Now, conservation of energy and matter is a very, very powerful principle. It will turn out in our work on Albert Einstein in coming weeks and months. We will use this conservation law to cast some new light, throw some new light on some rather puzzling things that are thought to be going on in quantum mechanics, like simultaneous cats who are simultaneously dead and alive. But coming back to my first year at Harvard as a graduate student, I went around asking people a rather simple question, which is related to what I call the basic fundamental question that information philosophy, my information philosophy, tries to answer. And the question was, if the universe began, 10 billion years ago in a state of equilibrium, which is to say it had reached the state of maximum entropy, then it should, according to the second law, have been in an end state. It would have been maximum entropy. There's no further evolution possible. Later came to be called a heat death. So I asked, how could it be that we, in 1958, were talking in Harvard about with information being exchanged between us in communication? Why was life possible if the universe began in thermal equilibrium? Why hasn't it remained in that end state of thermal equilibrium or thermodynamic equilibrium? Seems like a simple question, but I never found, or not never, but I didn't find any friends, colleagues who seemed to be able to grasp this question even, never mind the possibility of an answer, until about 8 or 10 years later, in the mid-1960s, when I was taking a course with David Layzer. Professor Layzer was also the thesis advisor for my wife Holly, so we knew David very well. And I took a course in statistics and probability using Feller's great textbook, learned a lot about that. And of course, thermodynamics, the most sophisticated way to derive all the results of thermodynamics is through statistical mechanics, which is a more powerful tool than thermodynamics, which was a classical tool that was used with gross macroscopic variables like the temperature of an object, its mass, and things like its conductivity. And when we got to statistical mechanics, we no longer used just these macroscopic variables, but looked at the microscopic things that were going on. Collisions of atoms and molecules were first worked out by Ludwig Boltzmann in the late or second half of the 19th century. And statistical mechanics showed how the entropy, which thermodynamicists just used as a variable S, that was related to the temperature and how much heat had been put in or out of a particular volume of matter. With statistical mechanics, we now began to be able to calculate the entropy. Boltzmann did this work, and it was shown to depend on the number of phase-space cells in a volume, which is to say the number of spatial cells, as you could imagine them, plus the number of cells of higher and higher energy. Boltzmann worked out the relationship between a gas that's away from equilibrium and what causes or explains its path toward equilibrium, or its tendency towards equilibrium, as a description of the particles initially being in a very localized space or a special part of energy, and then finding that by random collisions they distribute themselves among all the possible cells or little volumes where they could be in what's called phase space, a combination of physical space, geometric space, and velocity or momentum space, where the different momenta correspond, higher and higher momenta correspond to higher and higher energies. So it also could be looked at as a distribution of energy or velocities of the particles. And James Clerk Maxwell first, and then Boltzmann had derived the expression for the mathematical distribution of velocities in equilibrium. So, okay, coming back to 58 and my studies with David Layzer, he too seemed to be very interested in this problem, and I'm not sure I ever had him sit down and explain his thinking to me, but I subsequently learned what it was and found that David had written a paper. I actually have a copy of the draft paper that went around in 1971, and let me just do this. It's just a TypeScript paper called The Arrow of Time. But that then led sometime later to 1975 now, an article called The Arrow of Time in Scientific American magazine. So let me come over to my page on David on my website, and let's read a few of the paragraphs and look at some of the diagrams that I've developed to explain David's thesis. Obviously, he's a Harvard cosmologist who in the 1960s made it clear that in an expanding universe, entropy would increase as required by the second law of thermodynamics, but that the maximum possible entropy of the universe might increase faster than the actual entropy increase, making room for the growth of order or information at the same time the entropy is increasing. Okay, so let me try to give you a kind of an insight into this radical view, which I find about a dozen other scientists have written about this process, which I'm about to explain by David Layzer. And all of them but one I can trace back to earlier articles by others who have referred to David Layzer. So I think my research, my biographical and literature research, has shown that this idea of lasers is unique to him. And one scientist, a very famous one, Roger Penrose, the great mathematical physicist, in his book, The Emperor's New Mind, describes this process, saying how this might be a standard account of how things worked in the early universe without mentioning David Layzer. But I will show that David Layzer and Roger Penrose attended a conference on the Arrow of Time in 1973 at Cornell, organized by Tommy Gold, another great astrophysicist, cosmologist who worked with Herman Bondi and developed the idea of the creative continuous universe theory, that there was no Big Bang origin. There was just a continuous creation model of the universe. We may touch on them. But let's come back to David Layzer and listen to what it is he's saying here. I can do that with a picture, I think best. And if I can fit this on my screen, which seems like it might work. Here we go. The idea is that as at the beginning of the universe, one of the very most important things that starts to happen essentially instantly within the first tiniest amount of time from which we can measure the beginning, the universe is in a state of expansion. And I'm going to try to say that the expansion is the fundamental driver of all other things that are curious in that they have a direction. For example, we just saw David's paper called The Arrow of Time. I will try to show that the arrow of time is a consequence of the expansion of the universe. So what David is saying is the universe begins, it's totally in a state of equilibrium, but immediately it begins to expand. Now, suppose that the expansion runs faster away from the possibility of all the particles re-randomizing themselves. a little hard to kind of picture that, and I wish I could have an animation for you. In fact, let me just go to David's paper on the arrow of time, scroll down a little bit, and he has a nice diagram, which I hope you can see, that in the first panel, he imagines a perfume bottle which has just been opened. And when we look closely, we see that, let's see, am I getting this up here for you? I think I am, and a little concerned. Okay, in the first bottle, a few particles of perfume have leaked out into the room. And people could probably start smelling perfume on the other side of the room. In the middle panel, it's halfway gone out, and in the final panel, it's all outside and inside equally. So if we were to zoom in on that third picture, we'd see that there are basically as many particles, the density of particles inside is about the same as the particle density outside, and we've reached equilibrium. Now at this point, the question becomes, would those particles, given enough time, possibly go back into the bottle if time could be reversed? And that was the origin of the question. Why does time seem to have a direction which goes toward more and more chaos, never backward towards lower entropy and more order, like having all the particles go back into the bottle? So going back to this diagram, we see that David imagines that the top line, called maximum possible entropy, corresponds to the gas or the particles of the universe, which are seen to be in some initially very random distribution. As soon as there's an expansion, that distribution is no longer the maximum possible entropy. If we were to have, for example, a box and a divider in the middle of the box, and all the particles of gas on one side, like the perfume, all inside the bottle, and if we opened up the bottle, or if we opened the box, it would take some time for the particles to go and completely fill the whole box. They would come from half of the box, and then they'd have to occupy the whole thing. There's a time there, which is sometimes called a relaxation time. How long does it take before the particles now have maximum entropy, have maximum disorder, so that we've lost all possible information and they're now randomly distributed throughout the entire volume? So for this maximum possible entropy to be the case, we'd like to have the relaxation time by which the dust and gas, or particles, or whatever we have at the beginning of the universe, are completely uniformly spread out. Now suppose the relaxation time, or the time in which they can completely randomize throughout all the volume of phase space, is slower than the time associated with the maximum possible entropy. We would then have a reduction. We'd have what I've shown here on this diagram, and I think I could probably expand it for you to see it a little bit. We would have negative entropy. That is called the difference between the maximum possible entropy and the actual entropy would be possible information, potential information, or mostly in thermodynamic terms, a possible negative entropy, where negative entropy is seen to be the amount by which the actual entropy is less than the maximum possible. Now, Claude Shannon, who basically gave us the mathematics of information, always showed, or he did show, that it was strongly connected to the idea of entropy. The formula for information was essentially the same shape mathematically as the formula for entropy. And so today we mostly accept the idea that where there is negative entropy, there's a possibility that information structures can form. And of course, what are those information structures? In our picture of the universe, They will be initially in the early first 3 minutes of the universe. The great book On the First 3 Minutes by Steve Weinberg details how at the highest temperatures in the earliest moments, there's no matter that we would recognize because atoms cannot form until something of the order of 380,000, 400,000 years, because prior to that, the temperature is too high for an atom to stay bound, an electron bound to a proton. And at the very earliest times, even the protons and neutrons are being broken apart by the high energy radiation of the time, and they're falling back into being quarks. Quarks and electrons would have been the only things around at a very early time. So as Layzer's picture goes, there comes a time when atoms form, and there comes a time when the galaxies and stars and planets can form. But when they do form, it's because there's room for them between the actual entropy, which is the disorder of the universe, and the maximum possible disorder, which is not being realized because there are orderly information structures coming into the universe, and they occupy, in a sense, in this diagram, the difference between the maximum possible entropy, where there would be no structures visible to us, and the actual entropy we have in the universe. So let me just go back to a paragraph here. Layzer pointed out, let me go take that to full screen for you. Layzer pointed out that the equilibration rate, that's that relaxation rate, the timing it takes to get back into equilibrium for the matter was slower than the rate of expansion. This is his great insight. Then the negative entropy, defined as the difference between the maximum possible entropy and the actual entropy, would increase. Claude Shannon had identified this negative entropy with information, though the visible structural information in the universe may be less than this total potential information. Okay, and in this diagram we basically are going to say that its maximum entropy was very low at the beginning of the universe, and as it expands, the number of possible states in phase space grows rapidly. The nucleogenesis in the Big Bang creates particulate matter, but the maximum possible entropy goes faster than the energy and the matter can re-equilibrate, come back into thermodynamic equilibrium. And as we showed, the atoms formed at 380,000 years, and then after 400 million years, the galaxies, stars, and planets form. And then in the last few billion years, life forms appear, which are dependent on a radiant stream of negative entropy from the sun. So let me come back to say that in order for life to exist, there has to be a situation in the universe where we are away from maximum entropy, maximum disorder. And famously, Erwin Schrödinger, in his classic essay, What is Life, that he wrote in 1944, he argued that all of life is dependent on a stream of negative entropy. He described it as life feeding on negative entropy. And there's a little story about Schrödinger, who, when he was a young man, his dad had studied chemistry and was somewhat of a scientist, and explained to the young Erwin that he had learned that where others said that our life depends on the material, the food that we eat, that Erwin's father told him, it is not just the matter, we also need energy. And so it's matter and energy together that keep us alive. Well, Erwin went off to university and then graduate school and learned a great deal about thermodynamics, and came back after his studies and told his father, well, you know, Dad, it's not just matter and energy. And he must have known, as I introduced at the top of the hour, that the matter and energy are conserved quantities. There is another property called entropy, or particularly negative entropy, which is a measure of how much available energy there is in the matter or the energy coming through. How much of this stream of matter and energy available to us is can be used for maintenance of our living structures, cells and so forth. So in What is Life, he writes the story that it's actually negative entropy that's important. And he realizes that flow of negative entropy comes from the sun. I've always thought that very important, and back when I was first a graduate student, I said, well, we do have pockets of negative entropy in the universe, and how did they come about? Because although Schrödinger can tell us that life depends on negative entropy, and it comes from the sun, my question always raised was, how could some part of the universe provide negative entropy? How could that have come about when the second law of thermodynamics says that the entropy is always increasing? The answer must be, I thought in those days, that the overall entropy might be increasing, because as we see, the actual entropy is always increasing in the universe. But it could be that although the total entropy is getting higher at all times, and that would satisfy the second law, that we'd have this constant increase in the actual entropy. But we might also have pockets of negative entropy. And in my diagram, I've shown that maybe the negative entropy possibilities may be almost as large as the actual entropy that we have. And quantitative calculations are beyond my level anyway, but I called these pockets of negative entropy information today in my information philosophy. Without them, we could not be doing what we're doing today, because we're communicating information, and at some level we are creating information. Minimally, we're maintaining the information in our bodies, but maximally, we're also exchanging information, communicating it over the internet, hopefully changing your thinking or giving you some new way to think about how the universe fits together and where we fit into it. I believe there's a continuous story from the beginning of time in which there's a battle between the second law of thermodynamics, which basically wants to increase the disorder everywhere. Norbert Wiener, the great MIT mathematician and physicist, called entropy the, quote, devil incarnate, as if it was sort of the core idea of what evil is, that it's destroying everything of interest. And so on the other hand, this negative entropy that I thought was so important, and I wondered if I could ever describe what it is that brings negative entropy into the universe, and it should be thought of as not evil, but perhaps as a good, perhaps as an objective good, a sine qua non, without which no possibility for anything interesting would exist in the universe. Now, if we had a universe that was full of disorder and nothing else, we wouldn't be able to even think about the universe. But given pockets of negative entropy, which I thought might be a kind of a good, a precondition for anything good, a precondition that would allow, say, life to exist someday. I then, over the years and in recent years, have put together a story that the processes in the universe that are able to generate negative entropy, pockets of negative entropy, or information structures, as I call them now, were very, very few. The physical forces, four forces we're famously familiar with, like the nuclear and the electronic and weak interactions, and then this very, very weak gravitational force, all of them have the capability of creating some kind of order. Right at the get-go, the fact that the elementary particles can form nuclear particles, the nuclear particles with an electron can form atoms at 380,000 years, as we saw there. And then the weak gravity will become a force that can pull dust and gas clouds that look pretty chaotic and nothing very interesting going on into wonderfully spherical stars or planets. If the large enough mass is involved, they will heat up and they'll bring this bright light, which turns out to be our source of negative entropy that supports life on Earth. Let me take us back for a moment to that time here when the universe was just about to form atoms. Before that, the universe was dominated by radiation. There was so much light and so hot that if an electron and a proton did happen to get together, the incredible bright light, we're down to around several thousand degrees, about the temperature of the surface of the sun, that atom would be immediately ionized. If a molecule had existed and those would have been combinations of atoms, they would dissociate and then ionize, and so we would be right back to the nuclear particles. But just past this time, this 380,000 years, something very interesting happened. The temperature of the universe comes down, and it gets cooler than the surface of the sun, and it continues to cool and cool for hundreds of millions of years until we get to this point at 400 million years, where galaxies and stars start to form. At that time, the temperature of the universe is very cold, much colder than the surface of the Earth. Not just much less than the surface of the sun, but less than the surface of the Earth. And if we look out into the universe at that time, now there's no one there to look out, but should we imagine looking out at the universe at that time, it would have been very, very dark. Like our night sky? No, our night sky has stars in it. But in those hundreds of millions of years before the galaxies and the stars were capable of forming, when the universe had thinned out so that the average amount of matter was lower and lower and lower, and today it's so amazingly low, there's only about one hydrogen atom in a cubic meter. Now, this room I'm in is full of matter, and the Earth is, of course, very dense, 1 gram per cubic centimeter. But the average amount of matter in the universe today is only 1 hydrogen atom per cubic meter. So there's extremely small amount of matter, and it took a long time before the random variations in the matter in the universe were able to pull large lumps of that matter together into stars, planets, and galaxies. And at that time, we can say that the universe looked almost black in all directions. It wasn't as dark as it's called the cosmic microwave background, which is below 3 degrees Kelvin, but it was in the tens or hundreds of degrees and very dark, when suddenly the gravitational force pulled enough matter together that they could become a gravitating, self-gravitating object and coalesce and crunch one another with the gravitational force. In the case of a star, then, crunch it so hard that it would give off a lot of heat from just the forces of the particles banging into one another. And in their centers, they even got so hot, 20 million degrees, that the nuclear reactions began. And that's the source of light from all the stars, is this process of converting matter into radiant energy, which gave the stars lifetimes in the billions of years. Something that fills out my picture, that those stars that could live for billions of years could supply this out of equilibrium radiation. Remember, the equilibrium in the universe at that time is very cool, but here come these bright lights, and they form a flow of energy, photons, toward planets, and that will drive the creation of life. And if you think about the creation of the stars, galaxies, and planets as information structures, what you see is that when life begins, complicated molecules form very complicated information sequences, and they learn to duplicate themselves, replicate themselves, and they can do that ad infinitum the same, or they can make mistakes. Those mistakes are called variations. The variations then could lead to better information structures that are duplicating the information, and eventually they start to adapt in ways that some are much more successful at reproducing. And that's the beginning of the story of life, which is right up to human beings. We're still doing that basic creation of information structures, in which case, though, our information structures are using information to maintain ourselves. The cells contain DNA and processes that DNA drives and many, many coding type things that are going on. But it's still one story that goes back to the beginning of the universe when the first information structures could form. Okay, well, let's get back to David Layzer, who basically pulls this story together and gives us the driving force, if it's not a force really, but the process of expansion of the universe, which allows pockets of negative entropy. Those negative entropy pockets are what I call information structures. Some of them are passive. They just do what forces on them gravity causes them to do. There's nothing, no thinking going on, no information processing per se. But they will lead to the possibility of a planet on which information structures can start duplicating themselves until they become intelligent, like we are. So now there's some few paragraphs in here about David's work that I'd like to show this picture of increasing entropy and increasing information and contrast it to the way people thought just a couple hundred years ago. After Newton's time, the idea of the universe was that the total amount of information in the universe was a constant. Now remember, I've been telling you for some time now that information is not a conserved quantity, although some mathematicians do believe, still argue that it must be a conserved quantity like matter and energy. So in Laplace's view, which would be like some mathematicians, Roger Penrose may be one of them at some level, I draw a picture on the left side. It's information going up, and on the time here since the beginning of the universe. And the basic idea is if Laplace's demon can tell what is happening at all times, then the total amount of information is a constant. Whatever it is the demon would need to know about all the velocities and particles, that would be the amount of information. Now, in the middle of the 19th century, I say at the top, if information were a constant, there would be never anything new under the sun. So in the middle of the 19th century, thermodynamicists now, like Boltzmann and Lord Kelvin and others, decided that if the universe began with a large amount of information, it could then be explained that all the information we have now is being destroyed by the second law. So now we've got a starting point in the universe which has a lot of information, but it's heading toward what Hermann Helmholtz called a heat death of the universe. And a rather bleak picture. It was kind of discouraging to be a physicist in the 19th century. There are some mathematicians, I note here, who say that information lost to entropy might still be buried in the microscopic world, and maybe it could be recovered, for example, if you could turn time around, which unfortunately we can't do. So I then take you from that diagram to the diagram for David Layzer. And his notion that the entropy is going up, but the information is also going up. They're both going up. And now I just want to mention Roger Penrose again, because in his 1989 book, The Emperor's New Mind, Penrose speculated on a possible connection between information, entropy, and the arrow of time. Mind you, David had already written his article in '75, and so this is 14 years later, but we'll listen to Penrose here. Recall, he says, that the primordial fireball was a thermal state, a hot gas in expanding thermal equilibrium. Recall also that the term thermal equilibrium refers to a state of maximum entropy. This was how we referred to the maximum entropy state of a gas in a box. However, the second law demands that in its initial state, the entropy of our universe was at some sort of minimum, not a maximum. Now, Roger Penrose is reflecting the fact that maybe we should have had minimum entropy, that is to say, a lot of information. Now, Penrose, besides being a mathematician, is what's called a panpsychist. He believes there's something overall going on in the universe, like a cosmic consciousness and things which take him a little over the edge as far as I'm concerned. We've made a significant study of panpsychists and talked about one of them, David Chalmers, in our first lecture a few weeks ago. But now here's what I find to be quite interesting. What has gone wrong, says Penrose. One standard answer would run roughly as follows. True, the fireball was effectively in thermal equilibrium at the beginning, but the universe at that time was very tiny. Now that's a misconception. Our modern thinking is that the universe was perhaps always infinite, and that what really is going on at the beginning is simply that it's at a very high density, and that very high density is in all directions as far as we know, although there are arguments that pockets in the universe might be bubbles that inflate and expand. So let's see. I'm looking at our time here, and we're 20 minutes to go, but my clock is really telling me otherwise. Let me just take a moment to refresh this. And okay, 41, 20. Having a little trouble with my time, and here we are talking about the arrow of time. Let's continue with Penrose, where I think what he's doing is reflecting ideas that he may well have heard from David Layzer in 1973 at this Cornell conference on the arrow of time. So the fireball represented the state of maximum entropy that could be permitted for a universe of that tiny size, but the entropy so permitted would have been minute by comparison with the entropy which is allowed for a universe of the size that we find it to be today. And as the universe expanded, the permitted maximum entropy increased with the universe's size, but the actual entropy in the universe lagged well behind this permitted maximum. The second law arises because the actual entropy is always striving to catch up with this permitted maximum. And I hope you can see there my argument that what this is David Layzer's work. And I write, Penrose's standard answer is the work of David Layzer. Penrose met Layzer at this conference in 1973, which was just a few years after I got my PhD and was stepping away from Harvard. But it was, I have found since that time, this concept of the Layzer picture, and let me just go back to that picture. This picture I have found in perhaps at least a dozen different books. Most all of them seem to know that it came originally from David Layzer's work. And yet the one case of Roger Penrose is clearly describing that picture, but gives no reference to any of the other works. I think I can probably go down to Layzer in another page. Let me take us back to our home page for just a moment. And let me remind you, as I mentioned last time, I am now adding social media links. The very top links allow you to click and tweet your friends about this page or whatever page you're on. And the lower links, I just added this little Twitter link today, which this one goes to my Twitter account, this one to my Facebook account, and this one to my YouTube account, so that you can go there and follow me from those locations. I would appreciate that. Here I am scrolling down through all of my philosophers into my scientists. What I'd like to do is bring up another copy of my Layzer page. Here he is, next to Laplace. That's kind of interesting. And restart as planned. Countdown to goodness. Pick a time. I don't. hate to be having my computer restart in the middle of my presentation. Here I just want to go all the way to the bottom and show you my research, and there's a lot more I've said about David Layzer here, but I want to go to the bottom where I believe I have Layzer's papers, and maybe I have all of his papers available for you too. I'm going to click to the Scholar link on my web page and show you background information, a bibliography of important books on the subject of evolution as entropy, cosmic evolution, by Eric Chason, who was a Harvard graduate student also. These are works that are on evolution, but Stephen Frautschi especially has given full credit to David Layzer. And so, let's see, I have all of Layzer's papers here with references for you to find them, should you want to do so someday. Here's his book called Cosmo Genesis, which we've just been looking at. And all in all, I believe these are all the books I've been able to find that give us anything like this model of the increase in negative entropy as consistent with the second law. The second law, again, says that the overall entropy must go up. In order for the entropy to go down in some place, like when a star forms or when life forms or when life is doing its thing, maintaining itself, it must mean that somewhere else the entropy is going up. And the picture we have here from Layzer's picture, if we drill into it, in the case of Schrodinger's looking at life, we must say that the negative entropy coming from the sun is consumed. Part of it then is radiated away from ourselves or excreted in the form of matter, radiated away in the form of excess thermal energy, and that leaves the Earth. It goes towards heating the Earth, but eventually the Earth has got one side facing the sun and one side facing the night sky. And from looking at the night sky, we radiate thermal energy away into the depths of space and outward towards the huge, almost near vacuum of empty space. And that is a sort of a thermodynamic engine. Heat on one side, and from the sun coming in, and then notice that the radiation coming in from the sun is very hot. 5,000 degrees, it looks like the surface of the sun, but it's actually not as dense as the energy coming from the sun because it's been speeding out in all directions from the sun, and it's what's called its color temperature is 6,000 degrees like the sun, but its energy content temperature, the equivalent temperature of that energy, is down around 300 degrees Kelvin, or the average temperature of our planet. So this gives rise to a disequilibrium. We have a hot color of the light energy and a low energy density of that, and basically that hits the Earth and is taken up by living things and by the Earth. And as the Earth turns around and the light side then faces the dark night sky, I want this one here, that gets radiated away, and that's like any engine. A steam engine, for example, has a hot source and what's called a cold sink. And so our planet provides us with a kind of engine, and life is a living part of that engine. Something that David Layzer talks a little bit about, but not as particularly as I want to home in on a story that makes information very distinct from matter and energy. Matter and energy is being conserved, information is not conserved, but it is created on occasion where it has a source of negative entropy that can drive the creation of new information. So, let me see how much else I'd like to say. We have 10 minutes left to go. I hope to convince you that there is this is a rather deep scientific side of what I do as an information philosopher. And on Wednesdays we talk about philosophers and scientists. I'll mostly be talking about philosophers for quite a while because the big problems, the deep problems in philosophy and physics are mostly philosophy, at more than half of the book on great problems. And the last half of the book, though, tends to focus on quantum mechanics. And I have found a great deal of interest in quantum physics because of the role that Albert Einstein had in developing, even inventing, as I say, I believe Einstein invented most of the fundamental questions or issues that we face in quantum mechanics today. We'll be lecturing on those on Fridays, and on Thursdays I will be taking material out of my book Metaphysics, Problems, Paradoxes, and Puzzles, perhaps solved. And I want to remind you that these books, although they're available at Harvard Bookstore in Cambridge here or on Amazon, you need not buy them in order to participate, in order to read them and participate in our lectures. You know, these I want to be lectures like the ones I used to deliver, and at some time I hope to be able to develop the lectures. I've divided them into these 5 topic areas, Monday through Friday, but maybe those will become courses, lecture courses. Maybe we'll develop curriculum sort of materials, examinations, and some of you might like to test your understanding of what you're learning, either from the lectures, which are relatively thin compared to what's in the books, because talking for an hour is no substitute for reading a whole chapter and then coming back. And there may come a time when we can assign reading assignments and try to get together on working on an area where you do some work before you come to one of these lectures. So to help you know where what I'm doing and how I'm planning things, you should know that I am now maintaining my i5 blog, and let me go to that here. This is today's entry on the blog, which, if you were following this blog in some way, I'm not sure I know exactly how you actually subscribe to this blog. I should add that to my my opening page. Let's go back to my opening page for just a moment, the Information Philosopher. And I have here a link to go to my Twitter account, my Facebook account, and my YouTube account. But I really, down here in this search bar, remember that if you go to my search bar, you can put in a phrase or a name of anybody, and you'll get a search of the thousands of pages on the Information Philosopher website. Over here, I have a link I call Cite This Page, and you may not be able to read this, but it's saying cite the page in an APA style. Let me just click on that for a moment and see what happens. There we go. So it brings up the title of this page and retrieved date from Information Philosopher website. Now, those of you who are want to be doing scholarly work, you should know that, let's say we went to the Layzer page here and scrolled up to the top of this page. This is a very long page, so let me get my mouse over to the side. And in principle, this is a part of the website I designed and built over 15 years ago. If I cite this page, it says David Layzer, retrieved December 6th from Information Philosopher, and here's the website link for you to paste into your article on this subject. And I hope some of you who want to be scholars will take advantage of the fact that I've not only provided you all the resources, but I've given you a neat little tool to cite your sources. Now, the About is, of course, I'll open that in a new link and look here for a moment. Here you'll find the story, if it does come up, about my work. And lots of the things that went into being me that were not just the philosophy. But over here, back on the blog, here on December 6, 2017, we are doing David Layzer, The Origin of Information. And yesterday we did many forms of determinism and only one form of indeterminism and liberty and freedom and so forth. Now this blog, I have to post to the blog the videos, and I see I'm one behind. I haven't put the one up for the new menu or the one determinism, so I'm a little delinquent. I've got to learn to do these sort of housekeeping and make sure that I give you a source. In that case, the blog will be a chronological list, backwards chronological, like any blog, of what our lectures were, what the summary, the précis was for each lecture, and a link to the video. Now, if you had gone to, let's go to my main information philosopher page, close this. If you had gone to this new link that I just added today for following information philosopher, you would have gone to this page. What happens when you go to this page, it asks you to log in. And, oh, I have a new follower as of today. I only have 8 followers. Let's see, I'm not sure I'm covering the right material here for you. I'm sorry about that. This is the Twitter page where you could go and add yourself to my list of philosophers. This is my blog page where today's lecture entry is on David Layzer, previously on determinism, and so forth. And I need to figure out how to add a link to the home page that would let you go to the blog and perhaps put on a comment or show up there as someone interested in my work. Okay. So we are coming down to the last couple of minutes. Maybe I'll turn on my background music here and say thank you very much for being with me today as we looked at my Harvard colleague, David Layzer, who really taught me a great deal about the role of, well, shall we say, the formation of order in the universe. Here's his book again. And I owe a great deal to David, as does my wife, because she wrote her thesis on relativistic corrections to atomic energy levels under David's guidance. So for tomorrow, we look to a lecture out of metaphysics, and I've been using metaphysics generally as an entry point into deeper physical questions. So the beginning of the week is always going to be problems mostly in philosophy, a lot on free will on Tuesdays because that's my big first book and where I've done a great deal of my research into the role of indeterminism in the world and driving the possibility for new information. Claude Shannon showed that unless we had a lot of possibilities, we cannot create new information. If there's only one possibility, then information is a constant. No new information ever occurs, nothing new under the sun. And Wednesdays we'll discuss a philosopher or a scientist. Thursdays we'll take a problem in metaphysics and try to go more deeply into the possible deep physics understanding of reality that comes from quantum physics. And on Friday we'll go to look again at Albert Einstein and his contributions to quantum mechanics, which I think in some cases will give us a good way to think about these things. So again, thank you very much for being with me today. And I'll turn the sound down a little bit. Bye-bye.